Hi, my name is Sofia Spatharioti, and I'm here to present our work on using open data to automatically generate localized analogies. Imagine you're reading the news and come across statements like these. How easily can you understand figures like 1.1 million hectares, or 31,254 hectares, or 2 million people? Would you be able to detect that the area burned in Greece was wildly incorrect? In fact, it was much larger, 131,254 hectares. Prior research suggests that comprehension can be improved by using perspectives or analogies that make numbers easier to understand, as these papers show. So, for example, the area burned in Europe can be re-expressed as about half as large as New Jersey. The area in Greece is about the city of Los Angeles, and we can imagine 2 million people as having the entire borough of Manhattan without access to piped water. The challenge thus becomes, how can we find good reference objects? But there is a problem with this approach. Good perspectives need to be familiar to the reader, but people living in different places are familiar with different things. Some objects are standard and widely familiar, like a credit card, and other things are unique and narrowly familiar. The St. Louis Arch is a good height analogy for people in St. Louis, but not for most people elsewhere. Many things are not widely experienced. New Jersey, Los Angeles, and Manhattan are very US-centric and not ideal for people unfamiliar with major metropolitan areas in the US. Prior approaches have relied on crowdsourcing reference objects and building domain-specific models for each national and linguistic audience. However, such approaches may be difficult to scale, and the characteristics of the crowd involved may influence the types of reference objects we get. For example, a US-based crowd may consider Manhattan as a good analogy for 2 million people, but would that work for people in French or European audiences? Perhaps Paris is a better option. Thus, adapting analogies to different audiences may require a separate process for each audience. So how do we approach this problem? First, we identify a good source for candidate objects for our analogies. We also need to identify information that can act as proxies for helpfulness and familiarity. Then we can create a training set with crowdsourced ratings and identify which proxies are best for our purposes. Finally, we can train our model to generate ratings and identify the best objects for different measurements. We also want our approach to have the capacity to adapt to different audiences. For candidate objects, we looked at Wikidata. Wikidata is a free and open source knowledge base. It is actively maintained and is also multilingual. With more than 300 currently active editions, this gives us access to localized names, descriptions, links to external pages, etc. To create our initial dataset, we queried Wikidata for items that have some measurement attached. We then consolidated units, and we also consolidated cases where instances refer to the same type of object. For example, multiple different names of instances describing ships. Finally, we filtered out items from obscure and highly specific instances like hypogeums. That gives us an initial dataset of about 40,000 Wikidata objects with measurements attached from 60 distinct categories. We then considered 4 different proxies for familiarity and helpfulness: search volume, n-gram counts, text embeddings, and Wikipedia page views. For search volume, we looked at the estimated total number of results we get by querying for the object name using the Bing Search Engine API. The benefits here are that we have broad coverage, large scale, but we have to deal with entity ambiguity, along with data quality issues due to estimates. Now, what is entity ambiguity? Consider the following 2 entities. The first refers to United States of America, the country. The second refers to America, a 2016 sculpture depicting a toilet made of solid gold. Now, querying for the estimated total number of results for the second item may yield incorrect results, as some or most pages may relate to the first entity. For n-gram counts, we look at Google n-gram counts expressed as normalized frequencies. Here we have a familiar, well-defined corpus, but we still have to deal with entity ambiguity at a medium computation cost. For text embeddings, we use sentence embeddings with SBIRT. Here we get broad coverage and high dimensionality, but we still have entity ambiguity at a medium computation cost. Finally, we look at the average number of monthly views on the English Wikipedia for our last proxy. Here we have precise entities, because there is a one-to-one link between a Wikidata item and a Wikipedia page. Also, although to some extent present in the other proxies, Wikipedia gives us the most potential for cross-cultural information. Again, we have to consider a medium to low computation cost. We have established possible proxies for helpfulness and familiarity. But how do we evaluate good models for our purposes? Ideally, we would have human assessments for all 40,000 objects in our initial dataset, but that would be very cost-intensive. To solve this issue, we aim to generate a smaller subset with crowdsourced labels by creating a stratified sample of objects. We first considered clusters of objects based on the distinct instance they belong to. So city, highway, skyscraper, lakes, etc. Then, for each of these 60 distinct instances in our set, we picked the top 5 items in terms of monthly Wikipedia page views to collect assessments. This way, we can form a subset of 300 objects that we can use to feed and evaluate our models in a way that provides broad coverage while also mitigating issues from dominant categories and filtering out a lot of encyclopedic items that would not realistically be helpful. Here you can see some examples of the objects in our subset for different dimensions and how there is a mix of well-known and lesser-known items. You can find more details on the process we followed for collecting crowd ratings for these items in the paper. To evaluate our features, we fit a cross-validated linear model with L1 regularization. We compared all possible combinations of candidate proxies, and for each combination, we conducted 100 random training test splits and averaged the Spearman's rank correlation coefficient between predicted and human ratings. Looking at the results, we found that models with Wikipedia information outperform models without. Surprisingly, we also observed that a simple model with only Wikipedia information achieved comparable performance to models with additional features for both metrics. From this, we concluded that the other proxies can be safely ignored, greatly simplifying the modeling process. Finally, we averaged the helpfulness and familiarity predicted ratings into one model rating and refit a model over all of the label data, which we use for subsequent evaluations. Moving on to our model evaluation, we wanted to look at 2 things. First, how effectively does the trained model scale to different measurement types? And second, how effectively does the trained model tailor examples to global audiences? For the first, we consider new measurements for types that are known to the model: area, mass, height, and length. We also consider a type of measurement which the model has not been trained on: population. We create an evaluation dataset of 75 analogies following again a stratified strategy, and we crowdsource human ratings on Amazon Mechanical Turk. For performance, we look at the Spearman rank correlation between human and model ratings. Our model achieved an overall score of 0.77, and looking at individual attribute categories, we see our model can surface high-quality objects in accordance to human assessments, like United States of America, New York City, and Japan for area, or Mount Everest and Taj Mahal for height. Interestingly, we found the best performance for population, for which we had no training examples in our model. Examples here are NYC, the UK, and Iceland. Overall, we found that our model has a good performance despite the small dataset. We found an ability to generalize to new domains, and also the ability to highlight top-rated items even in domains with lower performance. Moving on to audience adaptability, we explore the effectiveness of our model towards adapting to different audiences by examining crowd preferences between the United States and France. More specifically, we designed a task in which participants from both countries were presented with a measurement and 2 reference objects and asked to pick the one that would be the most helpful to them in understanding the measurement. The options were chosen to reflect the top-ranked object from our model for that audience, using the Wikipedia edition most closely related to that audience, so English Wikipedia for US and French Wikipedia for France. We again followed a stratified strategy for picking a set of measurements for our tasks to ensure broad coverage. You can find more details about the process in the paper. Here is an example of what one of the 16 tasks look like, with instructions appropriately translated for each audience. For 11,000 square miles, the top suggestion for US audiences was Hawaii, and the top suggestion for French audiences was Belgium. The order of appearance for both the options and the measurements was random for all participants. We found that participants significantly preferred the model suggestions that were tailored to their specific audience. We conducted a mixed effects logistic regression with fixed effects for the location of the participants, whether they are non-US or US, and random effects for the participants and the questions, which revealed a statistically significant fixed effect of the audience location on the likelihood of choosing the non-US option. The preference per specific measurement gives additional insights. For example, our model suggests a French car for French audiences and a US car for US audiences. We also observed items that may be useful across multiple audiences, such as Hawaii, a globally known and popular travel destination, which is reflected in the percentage of responses for both audiences. To sum up, we developed a low-complexity open data model that we find is capable of surfacing high-quality perspectives. The model is able to adapt both to additional measurements and audiences without retraining. We found that Wikipedia traffic can aid in creating more inclusive experiences. However, we note that existing knowledge bases need additional information to identify helpful reference objects. In terms of limitations in future work, there is still a challenge in further discerning audiences whose language is the same. For example, discerning traffic between US and UK, or Portugal and Brazil. For future work, we could incorporate additional user information like proximity to user. We also have to consider lack of coverage and/or biases in Wikipedia articles, which may lead to gaps for underrepresented groups. Here, we can consider targeted crowdsourcing to recover culturally relevant items, among other approaches. We are also potentially missing common everyday objects for which crowdsourcing may also be beneficial. Finally, we do not consider context adaptability in this work. Following the encouraging results identified in evaluation studies, we undertook a more systematic collection of reference objects. This resulted in a dataset of 400,000 Wikidata items with measurements and ratings based on English Wikipedia, which we released to the public. Adapting this set to other audiences simply requires collecting Wikipedia information for the corresponding edition article. Thank you for watching, and feel free to reach out to me or Dan and Jake for more questions.